Welcome to another episode of Mustang Physics Screencasts. Today we're talking about interval problems and how to solve them. We've got to start with this reminder about the acceleration equations. There are 5 different equations that relate to acceleration. Yes, even this one that doesn't have acceleration in it is in fact an acceleration equation because if you've got a VI and a VF that are different, that object must be accelerating. In any case, any of these 5 equations and any of the equations we could derive from those 5 equations only work if the acceleration is uniform. In other words, the acceleration has one value while the motion is going on. Of course, that's how we know to break up an interval. We break problems up into intervals because the acceleration has changed. And what that means then, combining those 2 pieces of information, is we can only use each equation within one interval at a time and not overcross multiple intervals. Let's show you an example of some motion that should be broken into intervals. I'm going to bring in a movie from off screen. This movie is of Mr. Bradley and one of our student teachers a few years back, and she dropped a bowling ball and he caught it. Here you go. Now we have some screen grabs of that on the next page. Let's take a look. And you can see we made a velocity time graph. We actually fed that video into Logger Pro and clicked on the ball in each frame. Here is the velocity time graph of the motion. Here is a screen grab from the movie just at the moment that she released the bowling ball. And of course, here is the time where Bradley's actually catching it. Now, if we read the velocity time graph, you can see that the speed of the ball was 0. Then the speed of the ball became increasingly more negative until it reached a maximum speed of about negative 2.6 meters per second. This moment here, you can see the speed stopped becoming more negative and started trending back towards 0. That time from here to here, that's when Bradley is catching it. And of course, eventually it gets back to having 0 speed again. He's done catching it. So the catch is not instantaneous. The catch takes time. And the fall is, of course, not instantaneous. It takes time as well. If you can read really carefully, you can actually see that this acceleration is very close to negative 9.8 meters per second. That is the slope of this part of the velocity time graph. And that value shouldn't surprise you. It's the acceleration due to gravity, since air resistance is pretty negligible on a bowling ball as it falls. Now, this acceleration, the one that we can read from the slope here, is caused by gravity and Mr. Bradley, but because it's losing its speed, it's being pushed up harder than gravity is pulling down, and that's why Bradley here looks like he's straining a little bit. He's having to exert quite a lot of force to make the bowling ball stop. Now, you can see that the acceleration is reasonably uniform from here to here because it's a straight line. Now it has a slope, and that slope is equal to the acceleration that's caused by gravity. You can see that the acceleration is again uniform from here to here. Now that slope isn't as steep. Bradley is slowing it down more gradually than it was speeding up as it fell. But it's a different acceleration than as it fell. This slope and this slope are very different from each other, so we should break the problem up right there. So there's 2 intervals of motion, falling and stopping. Not uncommon for an object that falls. Eventually it's going to hit something and stop. Now, let's talk about that moment just a little bit more on the next slide. That moment right there is critical. That moment right there, if we read the speed at that moment and we find it to be about 2.6 meters per second. 2.6 meters per second then, that's VF of the fall. But it's also VI of stopping in Bradley's hands. The speed at the moment one interval turns into the next is a really important number because it's a piece of information that can be used in either one of the intervals, the one preceding it or the one that follows. If you have an interval problem and you don't know the speed at the moment one interval ends and the next interval begins, go find it if you can, because it allows you to then work on the next interval. Or if you're working backwards through the problem, it allows you to work on the previous interval. Let's take a look at a problem that might be written based on this motion on the next slide. So a bowling ball is dropped and Mr. Bradley catches it after it falls freely for 0.34 seconds. The ball comes to a stop in his hands as it moves down 0.48 meters. So if we wrote a problem like that and wanted to solve it, we'd start by diagramming the motion. Now, it says it's dropped. That means that VI of the ball is 0. Mr. Bradley catches it after it falls freely for 0.34 seconds. That means the 0.34 seconds isn't the time he's catching it, it's the time it's falling. So there is a period of time where the ball is falling, and that time is 0.34 seconds. Now, the fact that it is falling freely means it's under the influence of only gravity. Gravity causes an acceleration of negative 9.81 meters per second per second. The next part of the statement, starting here, the ball comes to a stop in his hands as it moves down 0.482 meters, means at the moment that Bradley first touched the ball, which would be right here, so this is where he first contacts the bowling ball. Then the ball moves an additional 0.482 meters in his hands. We should make that negative because the bowling ball ends up below where it started. The important thing here is that 0.482 meters is a part of the stop problem that happens after the fall. And what that means is we can't put this displacement, how far the ball moved while it's in his hands, together with this time or this acceleration, which is the acceleration and the time of the fall. They're two separate intervals. We can use our equations from here to here, and we can use our equations over again with different data from here to here. But we can't mix the two sets of data together because they're about different intervals, and the acceleration was different in those two intervals. There's one last piece of information, and that is that the ball comes to a stop. Of course, that's while it's in his hands, so that means right here, VF for the ball is 0 meters per second. Drawing a good diagram will help you to separate the intervals of motion. Because Bradley exerts a force, he pushes on the ball, that's going to cause a change in acceleration. That's how we knew to break the problem up right here when he first contacted the ball. Let's look at how to solve the problem. A says, find the final velocity of the ball just before Mr. Bradley catches it. Well, that is right here. If we knew enough information about the interval while it's stopping from here to here, we'd be looking for VI. But we only have two pieces of information, the displacement and VF. If we're looking for the speed right here, and we're going to calculate it from what happened beforehand, from here down, we'd be looking for VF, because that speed's at the end of that interval. And we have three pieces of information, VI, T, and AG, that are good in that interval. So the way to find VF for the fall, which is the moment before Bradley catches it, would be VF of the fall. Nothing wrong with using some extra subscripts to keep track of which interval you're talking about. Is A times T plus VI. So negative 9.81 meters per second times 0.34 seconds plus 0. Of course, when we calculate that, we're going to get negative 3.33 meters per second. For sig fig purposes, we'd call that negative 3.3 meters per second. Now let's take a look at part B of this problem. Find the acceleration of the ball as it comes to rest in Mr. Bradley's hand. Well, as it's coming to rest in Mr. Bradley's hand, that phrase is important. It tells us which interval we're looking at. That's here. Now, the acceleration as it was falling is already known. We're not being asked about the fall anymore. We're being asked about the part of the motion where the ball's stopping in his hand. So we need to now go about finding the acceleration during that time. We can reason through some things to start, and that is that acceleration is going to be positive because we know that the ball, as it's moving in that interval, is moving down, but we also know it's losing its speed, so the acceleration has to be up. In order to calculate the amount of acceleration, we need one more piece of data. But of course we have it. We just got it from part A. This important calculation that found us negative 3.335 meters per second is the speed right here. That's Vf for the fall, but that is the same moment as Vi for the stopping problem that follows. So now we've got Vi for the stop, 3.335 meters per second. We've got Vf for the time it's in his hands, and we've got distance, so we can pick an equation. The equation would be Vf squared minus Vi squared over 2 times the displacement will be the acceleration. Now, we have to be very careful with plus minus when we use this equation in this situation. I'm going to widen this so we can see a little bit better. And let's plug in these values with some particular care about what's positive and what's negative. Remember now, this is as it comes to rest in his hand. So Vf for that is 0. 0 meters per second. That thing squared is just 0. Minus whatever Vi squared is. But Vi is a negative 3.335, use the unrounded number, meters per second, that whole quantity squared. Divided by 2d, where 2 is just an integer, but d is negative 0.482 meters. Now, when you type this into your calculator, because the Vi is squared, that negative will get canceled when you square the number. Remember that you're also squaring the unit. This 0 squared, 0 times itself, cancels out. This negative is still there. It does not get canceled just because Vi is squared. However, it does get canceled with the negative in the distance because we're going to divide a negative number by another negative number, which gives us a positive. So the negatives all end up canceling out, and we end up with a positive acceleration as we reasoned to start. Now when you actually carry out the algebra, you end up with an acceleration of 11.54 ... and now this would be in meters per second. Now those values don't match up with what you saw in the screencast because we made up this problem to show you what kind of problem you might face that's not from a movie but rather from the text. A word problem, if you will, kind of like your homework problems. So zooming back out, what are the important takeaways here? The important takeaways are, if an object's acceleration changes like it did right here when Bradley first starts touching it, the speed at that moment is important. One thing I want you to notice is, even if we hadn't asked you to do part A, where you found the velocity of the ball at the end of the fall, you would have had to find the velocity at that spot to be able to do part B. So if we had just asked you for the acceleration of the ball as it came to rest in Mr. Bradley's hand, you would have had to have found the speed right here from the information in the previous interval so that then you could have worked on that next interval. If you're stuck in an interval problem, that's oftentimes the reason. See if there's at least one interval of motion where you have 3 pieces of information, or 2 if it's not accelerating, so that you can calculate the speed at the beginning or the end of that interval, which then allows you to work on the interval next to it, either preceding or following. Now, if you printed the notes, there are 3 slides with questions in them. One of them has a rocket-powered cart that flies across the room, and we want you to think about how many intervals this is. The next question has a woman trapped on the 5th floor of a building, and then she falls a certain distance, then she hits an airbag and goes another distance as she's slowing down with the airbag, and we ask you to find the velocity at the end of the fall. The next question is the same exact question, but then we're asking you to find the acceleration as she's impacting the bag. I hope that you see that question 3, and going back, question 2, is a lot like the fall and stop problem that we just did with the ball. Now, you can check with us for the answers, and if you'd like to try those 3 problems on your own, and then check with us, we'll let you know what the right answers are, and that can be a good self-check that you understand how to do basic interval problems. Remember, no matter how complicated the interval problems are, here's a summary of how to go about it. Break the motion into the number of intervals that actually exist in that motion. Remember, every time the acceleration of an object changes, usually because it came into contact with a new object or it stopped being in contact with some object, then it's a new interval. Be sure to use all of our kinematics equations only within one interval at a time. You can't use them over 2 intervals. There is one note exception. V average equals d over t can be used across multiple intervals because it's not related to acceleration. Remember that if you get stuck in an interval problem and there's not enough information about an interval to find out more, you might be able to find VF of the previous interval, which is VI for the interval you're working on, or you might be able to find VI for the following interval, which would be the VF of the current interval. One other real important understanding, if an object falls and then stops, or like a car, if it's moving and it comes in contact with a wall or another car and it ends up stopping, the initial velocity of that stop is not 0. The final velocity of that stop is 0. The initial velocity as an object comes to rest, even if it comes to rest very quickly, is whatever the final velocity was for the previous interval. So if you're driving along at 55 miles an hour and unfortunately you drive into a brick wall, VI of the time where you're touching the brick wall is 55 miles an hour. VF ends up being 0 not too much time later, which is of course why you would avoid doing that. Keep these tips in mind while you're solving interval problems and stay organized. A diagram helps to organize one interval from another and will help you from mixing the intervals together in your calculations. Good luck!